So hello everyone, we are now in week number 10, lesson number 2. So this should be 20th lecture, I guess. We are now almost 2/3 of the way done with the semesters. How exciting is that? I'm going to share my screen and inference about a population mean. And we talked about, of course, the conditions. It has to come from an SRS, has to be normal. Up until now, we dealt with when mu was known, and now we're dealing with when mu was, obviously mu is unknown, that's the whole point. We're trying to figure out what mu is, but it's more sigma. All right, up until now, sigma was known, and now sigma is unknown. And as a result, we don't use sigma over the squared of n because we don't know sigma, but rather we replace sigma with S, the sample standard deviation. We use that instead. And as a result of using the sample standard deviation, we have a little more uncertainty in our answer, so our confidence interval is just a little bit wider. And how do we figure out how wide? Well, instead of using Z star, we use T star, okay? And the T score versus the Z score, they're very similar. They both have X bar minus mu. They both divide the denominator by the square root of n. The difference is here we use sigma because we know it, and here we use S because we don't know it. One thing to be mindful of when it comes to T is that we have to know how many degrees of freedom we're going to use to figure out the right T for that problem. And we use n-1 degrees of freedom. So there's 20 data points, then we use 19 degrees of freedom, and so on. Other than that, we talked about the fact that the T distribution is a little lower and a little wider to account for this extra uncertainty, which is why the confidence interval is a little bigger. Notice as the degrees of freedom goes up, we get closer to being the standard normal. So 2 is down here, 9 it's up here, and if we can somehow get all the way to infinity, it would be the actual normal itself. Okay, so that's all we did last time. So the one sample T confidence interval, right, is the same essential formula as the one sample regular confidence interval. The difference is, of course, that we use T star instead of Z star, and we use S instead of sigma. Other than that, it's exactly the same. And I think we did this example in particular. I seem to recall doing it. So we certainly did this section. And then we have the one sample T test. And I think this might be new. Did we get this? Yeah, we did get this far because we did the match pairs and we finished this chapter. So this is a good review anyways. We had the one sample T test. Either you're testing mu being some value, and either it's greater than that value, or it's less than that value, or it's not equal to that value. And the p-value is the likelihood of being more extreme than what you actually got, what your test statistic is. So when you calculate your t, if it's a greater than, then it's the probability of being in this little region here, greater than your t-value. If it's less than, it's the probability of being less than what you got. And if it's not equal to, then it's the probability of being either on the far right or the far left, either one, okay? And again, Crunchit does everything for us. It's a wonderful resource which you have access to for your tests. Match pair t-test. And this is when you have a before and after, left hand, right hand. You have some kind of connection between your two samples. So rather than looking at it as two samples, which we haven't technically learned yet, we talk about the difference between the first and the second and use that, and then it goes back to the regular one sample t-test. And I remember doing this example about the chimpanzees. And then you have the robustness of the T procedure. Basically, as I mentioned before, either a confidence interval or a significance test is called robust if the confidence level or the p-value does not change very much when the conditions for the use of the procedure are violated. We know it has to be an SRS. We know it has to be a normal distribution for perfection. But what if it's not quite a normal distribution? What if it's not quite an SRS? So a sample is robust if it can if it can withstand those complications. Someone wrote something that said outliers too. Yeah, exactly. We know that you're not supposed to have any outliers for these tests to hold. And the question is, well, what if you do have outliers? What can you do then? If the procedure is robust enough, then don't worry about it. Use it anyways. Okay. The question is the T procedure so that robust that it can handle not being normal, that it can handle having outliers, or it can handle not coming from an SRS. Okay, because just because it's robust doesn't mean it can handle all of those. Okay, so we had this box here, which told us that the SRS is the most important condition more than anything else. It basically, it has to be an SRS. If it's an SRS, then even the T procedure is not robust enough to break that down. Okay, it's got to be robust. It's got to be an SRS. But what if it's not really normal, or if there's outliers? So if the sample size is less than 15, then as long as it's close to normal with no outliers, go ahead and use it. If it's at least 15, then I don't even care if there's outliers, or if it's strongly, well, sorry, I still care if there's outliers. I still care if it's strongly skewed. But other than that, don't worry about it. If it's moderately skewed or approximately normal, knock yourself out. And once we hit a sample size of greater than or equal to 40, then I don't even care if it's very skewed. You can go ahead and use it. Okay, and of course, very skewed distributions come along with outliers because the skewness usually incorporates those outliers as well. So that's all stuff that we did last time. Okay, so let's now jump to chapter 21, which is, once you understand the stuff that came before it, it's actually, the stuff that's coming now is actually very, very straightforward. Let's say you want to compare two different population means. So you want to compare, do men or women watch more TV every day? So you're going to do it, you're going to get a sample of men and see how much TV they watch. You're going to get a sample of women and see how much TV they watch. And then and you want to be able to compare these two to decide which one is greater. Do men or women make more money in a certain profession? Take a sample of men, take a sample of women, and compare them, etc. So what are the conditions? Well, just like for a single sample, it has to be an SRS. For two samples, they both have to be SRSs. Okay, so the whole SRS thing, that's like the most important. You got to make sure it's coming from an SRS. Before anything else, it's got to be SRS. We also want the samples to be independent. That means that neither sample should have any effect on the other one. Okay, one sample has no influence on the other. If it's a matched pair, of course, they're not going to be independent, right? If I match my before and after, obviously there's a connection between before and after. So we don't use matched pair for this scenario. How do you control it? So that's so Angel, when there's other variables in the background, you have to design your test in such a way to incorporate that. Maybe you do it per hour. Maybe you do it per day's worked. I mean, there's ways to account for that. My father was telling me recently that, there's a very famous result recently that male professors make more on average than female professors, which is true. You can't argue with the data. But then he told me to look a little deeper. I go, okay, what am I looking for? He said, if you actually look not at male versus female, but at departments, engineering and science professors tend to make more on average than English and sociology professors. And if you actually look at males and females in any given department, then they make roughly the same amount. So the reason why men make more on average is because which gender tends to dominate the scientific and engineering fields. Not necessarily saying it's a good thing, but which one tends to dominate the science and engineering fields. There tend to be more male professors in those fields. And which gender tends to dominate English, sociology, things of that nature. There tend to be more females in that field. And therefore, the reason why on average, at least at college, I'm not saying everywhere else it's the same thing, but at least at college, why men make more is because it's skewed more towards the engineering side. So I'm not claiming that there is gender equality. It's a whole nother issue. And I'm not claiming that there's not issues in that regard in other areas. What I'm saying is, as a statistician, sometimes you get a result and you have to interpret that result. And you have to ask yourself whether the result is giving you a conclusion that is valid based upon the true situation as opposed to a cursory glance. And of course, the more analytical you are, the more you understand, the more you learn, the better you are at doing that. Okay. And I mean, that's not necessarily related to this. I just, he mentioned it to me the other day. I thought it was a very important thing to say. Okay. Very important insight into statistics. So we don't do matching. Matching violates independence. Okay. With the matching, you do what we had last chapter, which is the match pair t-test. For this one, we need independence, and we also want both of them to be normal. Just like when you have one, we want an SRS in normal. When you have two, we want SRSs and we want them to be normal. Okay. And of course, because of robustness, as long as the sample sizes are large enough, then as long as there's no outliers and they're roughly the same, then everything's okay. In this class, any question that you're given is going to satisfy the conditions, because otherwise, what's the point? There's no math to do otherwise. So you have a population 1, and we label it by x1 for the first variable. It's got some mean, it's got some standard deviation. We have population 2. That's labeled by x2, the second variable. It's got some mean, it's got some standard deviation, mu2 and sigma 2. Okay. And quite often we're going to have the hypothesis test that we're curious whether or not one is bigger than the other, one is smaller than the other, or whether they're equal to each other. And we're going to relate that either by mu1 equals mu2 or mu1 minus mu2 equals 0. Because if mu1 minus mu2 equals 0, that's the same thing as saying mu1 equals mu2. Is there a bomb going off? What do you mean by that? Because it's so quiet, no one's talking? Oh, beeping in the background? I think my dad's making me my dinner. Salmon and cucumbers. That's what I've had for 5 days now in a row. I like it. Nothing wrong with that, but it's a little redundant. Dad, salmon and cucumbers tonight?
Yeah.
Okay, good.
In about a half hour.
Okay, good. I can handle that. Okay. So, hey, every little bit, right? Salmon's good. Now, what you're going to have is, of course, you're going to take 2 samples. You'll have a sample from population 1. You're going to have a sample from population 2. Each one is going to have its sample size. Each one is going to have its sample mean. Each one is going to have its sample standard deviation. And the question is, how do I put all these things together to come up with a result? Okay, so let's do this example here. Okay, this example here talks about, hey, look at this. Daily activity and obesity. What a shock. Okay. People gain weight when they take in more energy from food than they expend. James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity. Choose 20 healthy volunteers who do not exercise, and deliberately choose 10 who are lean and 10 who are mildly obese but still healthy. Attach sensors that monitor the subject's every move for 10 days. And this table here presents data on the time in minutes per day that the subjects spent standing or walking, sitting, and lying down. And the question is, do lean and obese people differ in the average time that they spend standing and walking? So the data we have here, 10 subjects who are lean, and this is how much time they spend standing or walking, sitting, lying down. And then we have 10 people who are obese, standing or walking, sitting, lying down. And what exactly is the question here? We want to know whether lean people spend more time standing and walking than obese people, right? Because if that's the case, then it's like, okay, all you got to do is walk more, stand more, and you should at least head in that direction. So we have the null hypothesis, the thing that we're testing against. right? The status quo is that, hey, there's no difference, right? The status quo is that everything is the same. mu1 equals mu2, right? We're testing to see whether or not mu1 is greater than mu2. So if I go to crunch it here, we see group 1, group 2, these are the 20 subjects. These are the times they spent standing, the time spent spitting, the time spent lying down. So statistics, T, because we don't know sigma here. So we use T. 1 sample, 2 sample, or paired.
Paired.
It's not paired, right? There's not a matched pair. There's not a before and after or a left hand, right hand. This is just 2 samples.
One sample. Because you're comparing two groups.
You're comparing 2 samples. You're comparing the first group to the second group. So 2 sample. The first sample would be the so let's see how to do this. Groups, group 1, group 2, group by group. There we go. Okay, group by group, group by group. Group 1 is the 1, group 2 is the 2. The data is the stand data. So the question is, do we want to pool the variance? Remember, we don't know sigma here. Okay, we do not know sigma, but the question is, even though we don't know it, do we think that they have the same sigmas? If we think they have the same sigmas, then we pool. If we don't think they have the same sigmas, then we don't. So let's see if they even mention that here. They don't mention anything about it. But when you look at their standard deviations, they're pretty far apart. So without any reason to think that we pool them, I would say that we don't. I'm looking for something here that says that we do, and I don't see any. So we're not going to pool them. So we're going to go back. And we're not going to pool them. Is this a 2-sided test or a 1-sided? Do we think the first one is bigger than mu2 in terms of their values, less than or not equal to? What are we testing against?
Greater than.
Greater than, right? We're testing to see if the first group spends more time is greater than. The null hypothesis says that the difference should be 0. So calculate. Okay. So the null hypothesis says the difference of the means is 0. The alternative hypothesis says the difference of the means is greater than 0. Group 1 has 10 people. Group 2 has 10 people. The sample mean for group 1 is 525.8. Sample mean for group 2 is 373.3. The standard deviations are given there as well. The degrees of freedom is 15.17. We'll have to see why that's the case. Okay, because remember last time we had n-1, correct? So where does 15.17 come from? Well, when there's 2 samples, it's a little more complicated. We'll get to that. The difference of the means, if you actually compute the difference of the means, you get 152.5. Our T-statistic is 3.808. And at the end of the day, it's the p-value that matters. What does the p-value tell you about this experiment?
To not reject the null hypothesis because it's less than 5%.
It's a small p-value, isn't it?
Yeah.
What do you do when it's a small p-value? You do reject the null hypothesis. Small p-values are very, very low likelihoods of me getting what I got if the null hypothesis were true. This is a 0.08% chance of occurring. And it happened. When something that unlikely happens, you got to question the validity of the null hypothesis. Okay, so in this case, we would reject the null hypothesis. And it appears that leaner people do stand more than more obese people. So I'm going to stand up for the rest of class. Oh, who am I kidding? I'm obese. I'm not going to. Okay. So welcome back. Okay. Oh, Leah, thank you for laughing at all my jokes. I do appreciate that. Okay. It makes me feel so much better inside. All right. So let's talk now about where these numbers come from. You're not obese, professor. It's just extra skin. Well, all things being equal, fat people use more soap. And if you want to save on soap, lose weight. That's what I say. All right. Just think. Yeah. I save on, I all the money that I save on shampoo, I spend on soap. So I'm really like, not really saving much. All right. Okay. And this big bone. That's right. Nothing but jokes from this guy. Nothing but jokes. How can the T-statistic be interpreted? That's a good question. Let's first calculate what the T-statistic is, how to get it, and then we'll interpret it. Okay, because it's a great question. How? Oh, thank you. Okay. So, first of all, here is the T-statistic formula. Okay. It is x1 bar minus x2 bar, the difference of means, divided by the square roots of s1 squared over n1 plus s2 squared over n2. Okay, that is the T-statistic. Essentially what it does is it incorporates the two samples together in ways that we're not going to worry about. This formula here, it can be derived. It's just, if at the end of the day you get to use a cheat sheet or you have a computer do it for you, it's just not really that important to understand why it's true. It doesn't really add anything to your understanding. But the T-statistic is essentially your result. When you got, in the last example, what do we got, 3.808? Right, is that what we got, 3.808? Was that our T-score, T-statistic? So if the center is 0 standard deviations, 1, 2, 3, 4. So you got a value about there, right? This is a T-statistic of 3.8. Now we are drawing this under the assumption that the null hypothesis is true, which is why the peak of the curve is right at 0. If the peak of the curve is right at 0, I would expect to get a value somewhere over here. My value was way out here in the wing. So my value, my T-statistic was far enough away from 0 for me to really question the null hypothesis is true and the center is 0. I think it's a lot more likely, if I had to make a guess, that the actual distribution looked like this and had its center somewhere near 3.8, because after all, that's what I got. Right? Much more likely to be this than the original. How unlikely? Well, 0.0008. So less than, less than 0.1%. Unlikely enough that I reject the null hypothesis. So that's what the T-statistic is. It's where you land on the bell curve. Okay, now, how many degrees of freedom? Well, without software, you take the smaller of the first sample minus 1 and the second sample minus 1. In our example, what was the first sample? How big was it? Well, 20 was total between the two of them. No, Angel. So 1 second. I want to go back a step. The green was the original curve if the null hypothesis were true. The red was it's probably more likely this. Okay. Yeah, so there's 10 of each. So there was 10 of each. So N1 was 10 and N2 was 10. So N1 minus 1 is 9 and N2 minus 1 is 9, which means that the degrees of freedom should have been 9 without software. But it wasn't 9, was it? What was the formula? What was the value? It was like 15 point something, right? 15.17. So where do they get that from? I don't even know if this book does it. This book might not even give it. I'm going to grab a book that I have here, and I'm just going to hold it up for you. You don't have to know it, but I'll just hold it up so you know where they're getting it from. So can you see that? Is that centered and in screen? I don't know if it is or not, because I can't see through my book.
Yeah.
Can you see it? Hello, anyone?
Yes, we could see it.
That is the actual formula to compute the number of degrees of freedom in this case. As you can see, hopefully, it's a very complicated formula. And that's the formula that the book, sorry, not the book, that the computer uses, because computers don't care how complicated a formula is. They just plug things in to get an answer. If you don't have software, then you just use 9. You take the smaller of the two numbers. Okay, so what exactly is the 2 sample T procedure? Let's take a look. 1, they got to be SRSs. I already mentioned that. They got to be normal. I already mentioned that. We don't know the means. We don't know sigmas, which is why we're using the S's. So we have these 2 formulas here. This is the confidence interval formula. The confidence interval is x1 bar minus x2. You should write this down. This is just a fact. x1 bar minus x2 bar plus or minus t star square root s1 squared over n1 plus s2 squared over n2. Don't forget, for t star, you always need a certain number of degrees of freedom. In our case, how many degrees of freedom do you use? Well, if you do not have computers, you use 9. And if you do have computers, then you use obviously 15.17. For the null hypothesis, for the testing of the null hypothesis, then this is my t-statistic. You see, it's very similar. Essentially, if you just take this guy here and divide by this, you get your t-statistic. So they're very, very connected. In fact, why don't we go ahead to the previous problem and do a confidence interval for it? Let's look at the same problem here. And this time, do a confidence interval. So 2 sample confidence interval, 95%. So this here, whoops. Uh-oh, that's not what I wanted to do. Where'd it go? This here is my confidence interval. Again, sample 1 is 10, sample 2 is 10, sample mean, deviation, degrees of freedom, difference of means, everything's the same. But rather than this whole t-statistic and p-value nonsense, in this case, it just gives me the 95% confidence interval. Someone interpret, please, what this confidence interval is telling me. That's a really large, yeah, it's a pretty big confidence interval. It is. What's it telling me? Hold on. The true mean lies within that interval. So you got to be a little careful here. There's not one mean, there's 2 means. So what do you mean the true mean lies within that interval when there's 2 different means? So it means the true difference between their means lies in that interval, or at least I'm fairly confident, excuse me, I'm fairly confident that the true difference between their means lies in that interval. What is missing from that interval that allows me to make my conclusion that the null hypothesis is wrong? What number in particular is not in that interval? There's one number whose absence from that interval tells me the null hypothesis is wrong. Which is what? No, not 525. 525 is just the mean of the first sample. I don't care about each one individually. It's all about the difference. What does the null hypothesis say the difference is?
0.
0. The null hypothesis says the difference is 0. Is 0 in that confidence interval? No. So because 0 is not in there, I'm 95% confident that it's between those two numbers, i.e. it's not 0. So my conclusion from the confidence intervals is really the same conclusion that I would make. Not that it's wrong. What is wrong? Nothing's wrong here. Well, I mean, you have a test. Your confidence interval, your hypothesis test makes you conclude something. Did you make a mistake? Maybe, maybe not. But there's nothing that's wrong. Your procedure is fine. You didn't do anything wrong. You just came to a conclusion. And the question is, what conclusion did you come to? Do you reject or not reject the null hypothesis? You reject it because the null hypothesis says that 0 should be in there. It's not. Reject the null hypothesis. So in terms of hypothesis testing and confidence intervals, we now have a new situation. But in terms of what you do, it's exactly the same. You just find on crunch it the right setting and you plug it in. So it's very, very straightforward in comparison to what we've already done. Robustness, again, they're just saying that it's robust. So the same robustness. In terms of test questions, robustness is more of a concept than it is to actually, than it is for mathematical questions. But essentially, if the sample sizes are large enough, then you can overcome not having normality and having skewness and things of that nature. For 21.7, it says avoid the pooled two-sample T procedure, right? So most software and graphing calculators, including Crunchit, obviously, talks about whether or not you want to pool or not pool. You only pool when you know that the variances are equal. If you don't know that, don't pool. And because you will never know it, don't pool. The only time it's okay to pool from a mathematical problem is that the problem specifically says the variances or the standard deviations, they might be unknown, but they're equal. If you know that, it's okay to use it. If you're given no information about that, then do not use it at all. Okay? I mean, it's very clear cut. Only use it if you're told that you can use it. Otherwise, don't. Okay? And all the inferences that we're making so far are about the mean. Okay? What if I want to make inferences about the standard deviation? What if I say, hey, I don't know my standard deviation, but I think it's here. Can I do a hypothesis test or a confidence interval for my standard deviation? And the answer is yes, but they're much more complicated. We don't use the Z and the T test. We use what's called the F test. And the F test is, first of all, it's mathematically more complicated, but who cares? We have Crunchit. What do we care how mathematically complicated it is? The problem is that the F test is much less robust than the T test, which means I don't think in this class we cover the F tests. I don't think so. We did Z, we did T, we'll do the chi-square. I do not believe we cover the F test. When I teach my 300 level stats classes, we certainly cover the F test, but I don't think we do so here. But the F test is used for inferences about sigma. I believe my standard deviation is this or that. We're not going to do those. We use means and proportions only. Okay, so this chapter is fairly quick, I think, because it's a lot of redundancy, a lot of the same thing applied to a new situation. And it's basically, here are the new formulas, now do exactly the same thing that you did before. And if we go to chapter 22, okay, it's going to be exactly the same thing. Okay, now we're talking about a population proportion. So what have we done so far? We did means and we did two means. We did means when we knew sigma. We did means when we don't know sigma. We did means for the difference of for a matched pair when we didn't know sigma. We did two means when we didn't know either sigma. So we spent a lot of time on means. Now, the other half of the situation is proportions. Okay, suppose I say I believe that LeBron James is a better free throw shooter than Michael Jordan. I'm not claiming he's a better basketball player. That's obvious, of course he is. But I'm just saying, I say he's a better free throw shooter than Michael Jordan. So what do? I'll probably take Michael Jordan's overall lifetime free throw shooting percentage and LeBron James's and compare them. And the question is, can I infer something from the data? Do I infer that one's better than the other, that they're not, that they're the same? What can I do? Okay. So everything we did so far is about means, but now we're going to do it about a population, about a proportion. So essentially, what does it come down to? We have to know the test statistic that we're going to use, the confidence interval formula that we're going to use, and the hypothesis testing formula that we're going to use. So first, what is the sample proportion? It's the number of successes divided by the number of trials. Okay, if I shoot a basket, let's say I'm learning how to play golf, and I want to know on a par 3, I want to know the likelihood that I hit the green in one shot. So I'll hit 2,673 golf balls from the same spot, or roughly the same spot, and let's say 170 of them hit the green. Okay, so I am a horrible golfer if that's the case. I've only hit the green 6.36% of the time. Okay, that is my sample proportion. We put a little hat symbol on top and we read it as p hat. The sample proportion is p hat. Okay, the question is, how well does p hat estimate p? If I actually want to know my true proportion, is that going to be in the vicinity of my sample proportion? My sample proportion is 0.0636. Is that in the vicinity of the true value? So this is the same thing that we did before for confidence intervals, for hypothesis testing, and so on. We are going to do a confidence interval test and a hypothesis test and determine whether or not what you can infer from p hats to p. So what do we do first? Well, as always, we draw an SRS. Okay, we draw a sample size, an SRS of size n from a large population that contains a proportion p of successes. Okay, p is the true value, which I do not know. I don't know p. That's the whole point. I want to infer something about p, but I don't know it. So I take my sample and I compute my sample proportion, the number of successes divided by the number of trials. So what is the expected value? What is the mean of my sample proportion? It's the same mean. I expect that my percentage of shots made is somewhere close or is exactly the same to the true value. I don't know, right? That's the whole point. Why would I take a sample and say, oh yeah, your proportion is 70%, and go, great, I think the true value is 40%. That doesn't make any sense. The whole point of taking your sample is so that your value you're going to use as your guesstimate for its value. So the mean of p hat is the actual p. And the standard deviation is no longer sigma. It's no longer s. It's given by this formula right here for mathematical reasons that we're not going to go into. It's the square root of p 1 minus p over n. Excuse me. That is the standard deviation for a sample proportion. As you can see here, as the sample size gets larger, what happens to the standard deviation as n gets larger? It gets smaller. The law, basically, it's the law of large numbers, right? The law of large numbers says that you hone in on the true value, because the standard deviation gets smaller. So it gets tighter, which means you get a sharp peak at that value. That's exactly it. Okay. And as the sample size increases, it becomes approximately normal. And the mean is P. And the standard deviation is the square root of P1 minus P over N. Okay. Does that make sense? Okay. Again, I'm not proving these formulas. That would take too much time and we don't have it. Okay. I am just giving them to you. It's understanding how to use them that matters. And that's what I'm going to illustrate next. So let's do a confidence interval, because at the end of the day, it's all about confidence intervals and hypothesis testing. So here is the confidence interval for a proportion. It's not X bar anymore because we're not dealing with means. We're dealing with proportions. So it's P hat, right? The sample proportion is P hat plus or minus Z star times the standard deviation, which is the square root of P1 minus P over N. Okay. Just like before, I'll write it just for comparison. Before we had X bar plus or minus Z star sigma over the square root of N. That's our confidence interval for means. This becomes P hat plus or minus Z star square root of P1 minus P over N. There's only one problem. We don't know P, right? The whole point of this is that we don't know P. So how do we use a formula that requires P if we don't know P? The answer is replace it with P hat. It's the best we can do. You don't know P, what's your best guesstimate for P? It's P hat, so use P hat instead. So the confidence interval for proportions, P hat plus or minus Z star square root of P hat 1 minus P hat over N. Write these formulas down, or at least this ending formula, so that when we use it in action, you'll understand where it comes from. Okay? This is what, again, just we're putting in the box. The large sample confidence interval for a population proportion requires an SRS. We don't know P. Can you scroll back to those formulas? You only did this one here at the end, which is the same thing. And this they're repeating it, so I don't have to scroll back. This is it. P hat plus or minus Z star square root of P hat 1 minus P hat over N. This is the confidence interval formula for a large sample. Use this only when the number of successes and failures are both at least 15. That is the condition for when you are allowed to use this. No, Simon?
In a few minutes, 2 or 3 minutes. It's not done yet.
But I'm hungry now. Anyway, so P hat plus or minus a Z star squared of P hat 1 minus P hat over N. Use it only when the number of successes and failures are at least 15. Yeah, he's okay, I guess. Yeah. Sure, why not? So let's do an example. The National AIDS Behavioral Study found that 170 of a sample of 2,673 adult heterosexuals had had multiple partners. That is, P hat equals 170 over 2673 equals 0.0636. What can we say about the population of all adult heterosexuals, right? What can you conclude from your sample about the entire population? So what's the plan here? We're going to give a 99% confidence interval. So let's go ahead and do it. Let's clear all this stuff. Let's clear this. Let's clear this. Statistics. This is going to be Z. Remember, it's a Z star, so we use Z, one sample. But this is for mean. We want proportions. So maybe proportions. Oh, here, proportions. There we go. Proportion, one sample. We're going to summarize. So N was 2,673. The number of successes was, why does it keep going down? 170. We're going to do a, what do we say, confidence interval? 99% confidence interval. So we go to confidence interval, 99%, and we calculate. So what does it give us? It gives us n. It gives us a total number. It gives us the number of successes, 170. It gives us p hat, the proportion, 0.06360. It gives us a standard error, which is, again, the standard error, SE, is this formula right here. This is the thing that we add and subtract, i.e. the margin of error, other than the Z star part. The margin of error contains the Z star. The standard error does not. Standard error is just this part. And at the end of the day, it gives us a 99% confidence interval. It says the true value of the proportion of adult heterosexuals who have had multiple partners is somewhere between 5.144% and 7.576%. That is the confidence interval. Okay, straight up crunch it, plug it in. What if instead I want to do a hypothesis test? So for a hypothesis test, you have to have a hypothesis. You got to say, I believe it's equal to this. What do you think the true value is of adult heterosexuals proportion who have had multiple sexual partners? What do you think the true value is? What do you think? 6%. Okay, so someone comes along and says, I believe, well, no, 0.0636 is not the true value. That's our sample value. We do not know the true value, right? We have no idea what the true value is. All we have is our sample. And we want to use the sample. No, we don't use it for P. No, 100% not. We use it for P hats. We use it for P hat. You plug that in here, you plug that in here, you plug that in here. But the whole question is, what is P? Okay, just say. Now, let's do a two-sided hypothesis test, because we're testing, is it really 0.06 or is it not really 0.06? And my value that I have two decimals in there, okay. My value that I get, so that's my data. So someone tell me, please, what I can conclude from that data.
You have a 43% chance of your sample having multiple partners.
No, that's not what a p-value gets you. That's not what a p-value gets you. The p-value does not give you that. The p-value is a number that you use to determine whether or not your null hypothesis is correct or not. The p-value is, we certainly do not reject the null hypothesis, right? The p-value is not small. The p-value is the likelihood of getting the result that you got, which was 0.0636, or something even more extreme, if the null hypothesis were true. If the null hypothesis was true, I'd have a 43% chance of getting what I got. Is that a likelihood that it's so small that I say, the null hypothesis isn't true? Come on, 43% chance? Nah, that would never happen. Of course not. 43%, it's like 50-50. So you do not reject the null hypothesis if the null hypothesis were truly 6%. Notice again, by the way, for the confidence interval, if I go back to the confidence interval, notice what is inside this interval. What is inside that interval? Well, of course, p hat is. I mean, p hat's going to be the center of your interval, but what number is going to be inside that interval?
6%.
6%. How are you going to reject 6% if it's right in your confidence interval? Does that make sense? I hope it makes sense. Makes sense in my head, and that's really what matters. Well, actually, it should make sense in your head. That's really what should matter. But notice, other than new formulas, the concepts behind it are the same. The concepts behind it are p-values, test statistics, confidence intervals, hypothesis testing, all the same ideas that we've done before. It's exactly the same thing. Now, we covered 1.5 chapters today. I was thinking of covering 2 full chapters, but I don't want to get so far ahead, and I don't want to give you guys a lot of homework in one weekend. So we're actually going to stop here. I think we've covered a lot today. But I'm going to stick around to answer questions if anyone has any on this material. You do not need to know the formulas if you use Crunch It, right? You plug things into Crunch It, and it pops out formulas for you. You have to know how to interpret the formulas. Right? That's the key. How do I interpret the formulas?
Professor?
Yes.
So since we finished the chapter 21 and chapter like 20, is that also due before the 31st? Or are you still giving us?
No. 21, 31st is what? That's in 2 days, right?
Yeah.
But we didn't finish 21 till today, right?
Right. Okay. So you're still giving us a week.
Yeah. I give you a full week from when we finish a chapter. So 20, does it say the 21's doing the 31st right now?
No, I was just curious because the rest of the assignments are.
Well, I made all the old assignments due on the 31st.
Okay.
New assignments are due,
Okay. I see.
We're back on schedule.
All right.
A little behind, we're all caught up. Angel, you say, can you talk more about the curve given for 22.2? So where do you see 22.2? This one here? Oh, so I'm not sharing. So let me reshare. Hold on. Okay, so here's 22.2, correct? So here we have our normal curve. And under the assumption of the null hypothesis' validity, we're going to, yeah, you can go if you want. I'm going to keep talking, answering questions if people have them. But if you want to go, I'm not going to make you stay.
Did you write this down?
Not yet. Oh, no, I can throw it on here. Thank you, Dave.
Okay.
My salmon. And my quarter of a cucumber.
Actually, a third.
A third of a cucumber. Great. So when you look at this curve, the null hypothesis always has its claim in the middle. Okay, so the claim is that P is the true value of P is whatever this number is that is the center of my null hypothesis. My confidence interval is going to be from here to here. P hats or P plus or minus Z star P1 minus P over N to P minus Z star P1 minus P over N. Of course, in practice, I don't use P because I don't know it. So I use P star instead, or sorry, P hat instead. Okay, but conceptually it's the same idea. My confidence interval is from here to here. If I fall outside that confidence interval, that would be equivalent to me saying that the null hypothesis is probably not correct. Because if the null hypothesis was correct, I'd fall somewhere near it. So the critical regions, the rejection regions, the regions on the far right and left where you say, I think the null hypothesis is wrong, that's equivalent to being outside of your confidence interval. Does that make sense? So for P hat,
So if
hold on. So for P hat, confidence interval, you use P hat, hoping it's close enough to P, and the confidence interval holds the true value of P. Yeah, the idea is that the confidence interval, we're hoping, we have a certain amount of confidence that the true value is in there. We don't know if it's in there or not. We'll never know if it's in there or not. But we have a certain amount of confidence that it's in there. So at 95% confidence, I'd say, I'm 95% confident that it's between here and here. Okay, or I'm 90% confident that it's between here and here, or 99% confident, and so on. So P hat is going to be the center of my confidence interval, because think about it. Out of all the possible guesses that you can make for P, the most likely is your P hat, right? That is the most likely possible guesstimate for P, is P hat. Do you agree with that? That makes sense, right? So that's going to be the center of your confidence interval, is going to be P hat. And then you add or subtract a given amount, and that creates this interval. And then I say I have a certain amount of confidence the true value is somewhere in that interval. My value is the center of that interval, but I'm not going to claim that that the true value is my value. It's the best guess, of course, but how do I know it's a true value? You don't. You never will. So what do you do instead? You make an interval, and you say, I'm really, really confident that it's somewhere between there and there. Does that make sense? Yes, no, maybe so?
I had a quick question. You know how so we would use the p-value that we would get from crunch it to find out if we reject or don't reject, and then we just see based on this curve.
You don't have to do the curve.
Oh, you don't have to do the curve if you just know.
Yeah, the curve is just like a conceptual understanding of what's going on.
Oh, to see if it falls within that curve or not.
Yeah, I mean, that's basically what's happening from a conceptual standpoint. The p-value is all you need. If the p-value is less than 5% or whatever your cutoff is, you reject. And if it's not less than 5%, then you don't reject. Conceptually, what's occurring when you reject? Conceptually, what's occurring is that you are getting a result that's, depending if it's two-sided or not, on one side or the other. And if you get a result that's really far away on the left or really far away on the right, that's going to be the equivalent of getting a small p-value. And if you get something that's in the middle, that's the equivalent of getting a p-value that's not small enough to reject the null hypothesis. Does that make sense? Make more sense? Make a little bit of sense? Make any sense?
Would the p-value that we would use as kind of like our standard, would it be 0.05 unless it's given?
Not the p-value. The p-value comes from your experiment. The cutoff.
Yeah, the cutoff.
0.05 unless you're given something different.
So if it's above 0.05, then we would not reject.
Not reject. And if it's
Okay.
below 0.05, then we would reject. Yes, no, maybe so. Does that make sense or not? Anyone? Leanna says yes. Okay, good. Anyone else? Any other questions, please? Feel free to ask. I'm here to answer any question. It doesn't even got to be about math. Oh, that's right. I'm in a good mood right now. Not really, no. He said, could calculus help us? I really don't see how calculus would do anything here. I mean, some of the derivations might require calculus, but not in terms of like the practical solving problems.
All right, so that's it for me. Thank you, Professor. See you next week.
Yeah, it's got to be the salmon, right? So a mukbang. What the hell's a mukbang? What's a mukbang? A mukbang on your YouTube channel. What does that mean? What's a mukbang? Your video when you eat so people can see? What? So Gazal, I understand what you're saying. I can look for slides. Let me talk to my professor and see if he has any. And if he does, I'm more than happy to go back and use those. Or maybe in conjunction some way. I'm totally okay with that. Okay, problem. A mukbang? What does that term mukbang mean? Mukbang.
Basically, like a whole bunch of YouTubers record themselves eating and they get paid to do that and talk about like whatever they want. But the way they eat is just so like,
They get paid to eat?
yeah, and they try like different things.